I want to mention a variation on this disc method we've been discussing, and it involves a notion called a washer. Now, a disc is a solid. It's essentially it's a cylinder, but it is a very short cylinder, and it's laying on its side. And so we have the volume. The volume of this disc is pi times the radius squared times the height. That's the volume of any cylinder. Now, in this particular construction, if I call r of x the radius, and if I call delta x the thickness or the height, then in this particular case, this translates as the volume is pi times r of x quantity squared. It may be a specific number, it might be a variable expression, but whatever the radius is, it's that radius squared, and then the height is delta x. And so we saw that if you have several of these disks, then we can sum those volumes. And that leads to the Riemann sum, and that leads to the definite integral. Now we're going to take a look at a slightly different notion here. This is a washer, a hollowed out disc, some people say. It's a washer. It's a disc, but it's has a hole in it. It's like a washer you would put on a bolt when you're constructing something. And so the question here is, what is the volume of this washer? Well, if there were no hole drilled through it, the volume of this washer would be the same as the volume of the original disc. And so, the other question is, we can think of this washer as one cylinder with another cylinder taken out of it. Because out of this, we would have extracted. If you drill this piece out, you would have taken out a small little inside cylinder. And so the volume of this piece is the volume of the original, subtract the volume of the piece that we've cut out. And so if we call this distance capital R, the outer radius, and if we call this distance lowercase r of x, so that would be this distance, that's the inner radius. There's the outer radius and the inner radius. Now notice it doesn't matter on which side of the x-axis we fall. We could just as easily call this r of x, and we could just as easily call this, capital R of x, and this is little r of x. So it doesn't matter where we are, above or below the axis, that radius is the same whether it's above the axis or below. That's going to come into play later when we do these constructions. But the point is, the volume of the washer is the volume of the exterior disc. I'll say big volume minus the volume of this small piece that we took out, which is the small volume. Well, what is that? The volume of the larger is pi times r of x quantity squared. And in the same, if we're going to, again, use the same delta x for the thickness, well, the thickness of the original is the same as the thickness of the one we took out. And so pi times the radius squared times the height, or in this case we would call it thickness, that's the volume of the larger disc. Subtract off pi times the smaller radius squared times the thickness. And we can rewrite that because I'm going to factor out the pi and I'm going to factor out delta x from this expression. But when I do that, I'm going to factor out the pi to the front and factor out delta x to the right-hand side, to the back. And so if you can factor this to write this as pi, then we would have large radius squared, quantity squared, minus small radius, quantity squared, and I'm going to factor out delta x to the back, to the right-hand side. And so this expression gives us the volume of that washer. And that's going to come into play because what we're going to do, just like we took solids of revolution and broke them into a large collection of small disks to approximate the volume, now we're going to take a hollowed out solid of revolution, and use these washers as an estimate to construct that, and then use that as an estimate of the volume for that type of a shape. And so this is the volume of the disc. This is the volume of a washer. And as we can use this to find the volume of a solid, a complete solid of revolution, this is what we can use to find the volume of a hollowed out solid of revolution.